So, welcome back again. Our next speaker is Magnus Hagander. He's a core team member, Postgres committer, Postgres major contributor, everything about, he knows most of the things about Postgres. And now he's going to talk about Postgres 11 features. Thank you.
Thank you, Devin. Now we're on. Yes, technology. I'm going to say good morning even though it's noon because we consider it morning. I just want to make one more note for the record and for Devin before I get started, which is no. Yes. And then we're good to go. I'm here today to talk about Postgres 11. Who's already using Postgres 11? It's good. Who's already using Postgres 12? You guys are boring. So as Devin said, my name is Magnus Hagander. I work for a company called Red Pill Inpro. We're an open source services and consultancy business in the Scandinavian area. I'm out of our Stockholm office, where I work, primarily with databases, and unsurprisingly, that means Postgres in our case. That's kind of why I'm here. Within the Postgres project, I'm one of the core team members. I'm one of the committers on the database backend, and I do a lot of work for Postgres Europe, which is the non-profit that coordinates a lot of these activities across Europe. For one thing, our dev room here today and the PG day that we had on Friday, more downtown. But let's talk about Postgres 11. And let's talk about the new things in Postgres 11. Some of you have seen these things before. I do this sort of the new version of Postgres talk every now and then. The format's the same. Luckily, the content is different. There are actually new things in Postgres 11. And as with all Postgres releases, we go for approximately one release per year, targeted at release in September. What happens then is the Postgres 11 actually started in August of 2017 when we branched off Postgres version 10. At that point, we opened up the development of our master branch for what would become Postgres 11. Now in Postgres, everybody has their own names for everything. We work with something that we call commit fests, which is basically our way of doing iterative development, where we do, the idea is, I should say, because we all know how well plans work, but the idea is to do 1 month worth of building features, and then 1 month worth of reviewing and then committing these features. That's the commit fest. And then we just do rinse repeat that for 4 times, which, if you do the math, that's 8 months, not 12. But then it takes a while to stabilize it and get it out to be an actual release. So we started in August of 2017, and we finished in almost September 2018. Some people says it was October, but we can pretend that it was almost September. We're only less than a month late. Is not all that bad. So the release has been out since October of 2018, which is why I guess I'm actually surprised that so many people put their hand up for that you're already running Postgres 11. That's great news. Well, I hope it's great news. I hope it actually works for you. But that's actually unusually fast. About this far into release, I would normally see fewer people who are actually on this version and more people on the previous version. Anyway, let's get into the features that we want to talk about here. I've tried to separate them up a little bit into 4 sections. We've got DBA and administration, SQL and developer, backup and replication, and then just sort of performance, because everybody loves performance. And there's always new interesting performance things coming out. So let's start in the area of DBA and administration. First, what's the actual difference between DBA and developer today? Well, DBAs do development and developers do whatever, and DBAing. I just decided to split, saying, well, if it's used through SQL, then it's developer. And if it's config file and command line, then it's at DBA. So let's start with a small feature, or potentially big, depending on whether you need it. Those of you who worked with Postgres for a while have probably run into the fact that our transaction log, or our WAL, is made up of 16 megabyte files, and they're always 16 megabytes. And if you happen to generate a large amount of transactions. When you do your log archiving for backups, it sends the files off one by one, and if you generate many of these files every second, generate a few hundred megabytes in a second, that's a lot of overhead in just transmitting the files. You've actually been able to, I think, from the day that transaction log was added to Postgres, change the size of these files. You just had to recompile from source and get an incompatible data directory format, which you probably didn't want. 11 will let you configure this WAL segment size by, say, giving a parameter when you initialize the database. You still won't be able to change it once you've initialized your cluster, but at initial point you can set it. I would expect the normal use case for this is if you have a very high transaction rate system that generates lots of transaction log, you want this to be a higher number. You can also set it to be a lower number if you are really resource constrained and things like 32 megabytes of disk space is way too much. But most cases today when we're dealing with database servers, like 30 megabytes, it's really not that much. But there could be a use case for it. The next thing I want to mention is something that can potentially break your things, potentially. Who's using the plugin pgstat statements today? Okay, the rest of you should really look into the plugin pgstat statements. It's awesome. It gives you a lot of insight into what your system is actually doing in a very useful format. The pgstat statement tracks your most frequently used SQL queries in the system across time. And it hashes them and gives you something called a query ID, which uniquely identifies this query. Prior to version 11, this query ID was 32 bits. In 11, it's 64 bits. Normally, you don't really have to care, but particularly if you have a system that, for example, snapshots the data from this into monitoring to generate cross-time graphs or something, you need to update that system as well to support the 64-bit version. It really is that simple, but there are systems out there that break. It also means if you're using one of the more common tools around this, there are web visualization tools for pgstat statements, you just need to upgrade them. As far as I know, they've all released updated versions that support it, but you need to actually install that version. Otherwise, it doesn't help. We've added the ability to collect statistics on expression indexes. If you've been tweaking Postgres query tuning, you know about the command alter table set statistics. Because you get a better query plan, you tell Postgres, well, look at a bigger part of the data to build more detailed statistics to generate better query plans. And previously, you could only do that at the column level. So you could say, this column, we need to collect more data about this column to get better query plans. Making planning more expensive, trade-off for better query plans, right? The new thing in 11 is that you're now able to do this for expressional indexes. An expressional index is you create an index on, well, something that's an expression, so it's not actually a column. In this example here, created an index on x and then x, y, and z plus t. The last thing there is not a column. It's an expression. It could be a function call. It could do all sorts of different things. And previously, there was no way to tell Postgres to look more at that. The syntax for doing this is alter index and then alter column, and you actually give it the column ordinal in the index, so the third column in the index. Because columns and indexes don't have names. They just don't have names. When you do it on a table, you'd say alter index blah, alter column, my column. But since it doesn't have a name, you have to give it the number. Other than that, the statistics works the same. The default value is normally 100. You increase it, collect more data, analyze takes longer, query planning takes longer. Hopefully you get a better query plan. The other big thing that we've done to indexes is we now have something called include indexes. People used to other databases will also know the term covering index, for example. The idea here is that we can add columns to our index, making them less efficient. And of course, everybody wants less efficient indexes, right? The idea is we do this in order to be able to use an index-only scan. If you look at something like the example here, I have a unique index on my table. If I have a unique index, like my primary key, then obviously that index can be used to look up things in this column that's unique. If I want to be able to look up one more column by using an index-only scan, I can add this column to the index, but this becomes a problem because now the index is no longer unique on what I thought was my primary key. Right? It is now unique across both of the columns. And the difference with include indexes is when I say something like this, I say, create unique index using B-tree on ID means it's going to be a regular unique index on ID, and then I say include second field. It's going to add second field to the index for every row, but not to the key. So it's still unique only across ID, but any query referencing the ID and second field columns and no other columns can now be satisfied by an index-only scan, and you never have to look at the actual table. But as a regular index, this index just became less efficient because there's more data in it. Less data fits in cache. So it's a useful trade-off, but it's something to consider that the actual index does become less efficient. But the idea is trigger the index-only scans. Anyone using the PG pre-warm extension? Well, a couple of people, not too many. It comes in Postgres contrib. PG pre-warm's been around for a while. The idea behind PG pre-warm is, for example, if you need to restart your server, you can run PG pre-warm. It'll snapshot the information about what's in your cache. Because normally when you restart, your cache goes away. So you can tell pre-warm snapshot it, restart, and then load it back. And the thing that we can do now in Postgres 11 by setting this to automatic is we can have it just snapshot every 5 minutes. And if it crashes or you get a replication failover or something like this, it will automatically load the cache as it looked up to 5 minutes ago, which is normally good enough. Now what it does actually store, it doesn't dump your entire cache. So if you have 50 gigs of cache, it doesn't write 50 gigs of data. It just writes a list of which disk blocks were in the cache. Not the contents of them, just a list of them. So in particular in cases like recovering from replication failover and things like that, this can be a good way of saving this terrible performance blip you usually get when no data is in the cache anymore. We've added a bunch of new default roles. This is part of the steps towards getting rid of superuser. Well, not really getting rid of superuser, but getting rid of the need to use superuser. So we have 3 new roles: PG read server files, write server files, and execute server programs. They kind of tell you what they do, right? If you grant PG read server files to a user, they can read any file on the server, as long as the Postgres OS user has permissions on it. And if you grant PG execute server program, well, they can execute programs on your database server, which may not be the greatest idea. But it depends on who you're granting it to. And it's still better than superuser, because superuser can do all these things and more. So it's making these things more granular and making it possible to make a more secure installation. I think one of the most requested features in Postgres over many, many years, alter table add column. Who's ever accidentally done that in production and added the column with a not null and default and then looked at the downtime counter as the entire table was rewritten? Well, you can now actually add a column, not null, with a default, and it's more or less instant. Does no longer need to rewrite the table. Now, it does have to be a non-volatile function. You can't set things like current timestamp, because that would change over time. That would be very strange. But you can give it an actual default value. And what happens is that Postgres remembers this, and then as the table gets rewritten, either by you updating something else in the row, creates a new copy of the row, then it'll materialize the default value into that row. So eventually, it'll be like slow updating across the table, and eventually it will be just like it was before, but it does all of this without holding an exclusive lock and rewriting half your database and causing downtime and evil things. So that's, I'm sure everybody has made that mistake at some point. If you haven't, well, you will. And luckily, it will make much less effect now, as long as you set it up right. So let's take a look at some of the SQL side of things. Who's using Postgres full text search? Okay. Been enhanced further. In particular, it doesn't actually enhance the search itself, but we've previously had 2TS query, which takes a Postgres specific syntax, plain to TS query, which takes a plain text, phrase to TS query, which takes a phrase and turns these into the internal query syntax. Now we have web search to TS query, which takes what you expect and turns it into a search thing. Basically, it takes the syntaxes that we are used to using in search engines. So you can type foo and bar, you can use parentheses to group things, you can do not, you can do all these things in like free text mode. And it will parse those and turn it into a reasonable search query and then run that. So I would say almost in any case, if you're taking user input and doing a search based on it, which is not exactly an uncommon way of using full text search, you probably want to be using the web search to TS query, and it's a drop-in replacement. Of course, the syntax changes a bit for the user, but functionality, it's just passing the search term, run the search. It's kind of what you want in almost every case. The previous ones are, of course, there if you need the more control and if you need to be more specific about what you're doing. Postgres domains have been enhanced to basically do things that they couldn't do before. There were like little corner cases. You can now create an array of a domain, and you can create a domain over a composite type. So you can do a domain over an array, over a row, over an array, over a domain. Yeah, well, okay, don't do that. But basically, it's been one of those. There's a little one box that wasn't checked of things you could do with domains, and now you can do those things, which is always good. On the SQL side, the really biggest thing, I think, is full support for SQL 2011 window frame clauses, all of them. Our resident SQL standard expert has been telling me that we're actually, at this point, the only database that does that. Or at least we were, about half a year when I last saw him give that presentation. I don't know enough, but we do add a lot of them. In particular, the new added feature is the range between. Previously, we could only do rows between on the window clause. So it now handles values and not just row counts. And the fact that we have exclusion clauses, so we can exclude current rows, we can exclude ties and things like that. Of course, everybody knows exactly what that means, right? Okay, let's try an example. If you look at the first one, this is the classic, the way we used to do it, or one which we of course still do. We do select I, in this case is a silly table with 1, 3, 5, 7, 9, etc. Right? We say I, and then we say sum I over order by rows between 2 preceding and 2 following. That's what we've been able to do before, right? For each row, we declare a window that's the 2 rows prior to this row, and the 2 rows following it. And then we do a sum over those, and we get a running average or running sum across our data. So that's our column that gives us 9, 16, 25, etc. The different thing that we can do now is we can also say sum I over order by I range between 2 preceding and 2 following. So instead of looking at 2 rows, it will look at 2 values. So for any row here, if we look at, for example, the row 5, well, the 25 here is 1 plus 3 plus 5 plus 7 plus 9. The 15 comes from, well, it starts with the current row and goes backwards. It was like, oh, this one is 2 or less, okay, include. This one is not, so stop. And then the other way, so in this case, it's 3, 5, 7. Now, of course, if my data is this uniform, it's actually every second value. I could just say rows 1 before and 1 after. That would be smarter. But this lets you look at arbitrary data through that. And the exclusion thing that we can add is we can just say, well, also when you do this, just exclude the current row. Then you get the 2 before and the 2 after, but not the current one. And you can say exclude ties, which means you skip rows if they have the same value as the previous one. Things like that. So you can do that. One of the more interesting things around this, I think this is a more interesting example through it, is you can use any data type in Postgres that's sortable, basically, that has the B-tree operators as required. So in this case, we're saying select T, and then we're counting over order by T, range between 15 minutes preceding and 15 minutes following. So presumably T is a timestamp, right? So we're saying create a window of 15 minutes before us and after us and just run it across our entire data set and return the count. We can return any aggregates. We can return sums or averages or sort of anything like that. And we get data back like this. For every row, you can say, well, at this timestamp at 0013, going 15 minutes back and forth, there were 12 rows in our data. And it's with use cases like this that this feature starts to really pay off, and you can do really interesting analytics that previously required you to either write a stored procedure or copy all your data up into the application and just loop over it. And obviously this is going to be faster than either one of those ideas, because none of those is sort of ever going to be. So basically you have the count and the over. You always have to have an order by, otherwise it would be like, yes, please take me random data and give me a sum. That doesn't really help. You create the range, 15 minutes preceding, 15 minutes following, creates the window, and then it just runs the window across the data. The other big thing at the SQL level is stored procedures. And some of you have been around for a while. It's like, hey, didn't people used to say that the reason we should use Postgres instead of MySQL is that Postgres had stored procedures and MySQL didn't? Like back in the days when they didn't. I was like, yeah, people kind of said that, but Postgres never actually had stored procedures. Postgres had stored functions. Very similar, slightly different. The important thing, it uses the SQL standard syntax, so you can now say call instead of select. It's really important, right? It's the main thing. Now, the really interesting difference between stored procedures and stored functions is that stored functions runs inside of your transactions. Stored procedures can control your transaction. You can't do rollback or commit inside a stored function. You can do rollback and commit inside a stored procedure. The syntax and how you create it is very similar to how you create a function, except instead of saying create function, you say create procedure. And you don't have a return value the same way. Like you don't still return a result set in the same way. So if you look at this, we say begin, we say insert values 1, commit that, insert value 2, roll back that. Right? If you tried this in a stored function, you would just get a syntax error saying, sorry, you can't do this inside of a stored function. Now what you'd expect if you write this, right? You read that and you go like, well, if I call this stored procedure, the table should end up with just the 1, right? And the 2 would then be rolled back and gone. And if you do it, well, that's actually exactly what happens. So it does work the way you would expect it. It gives you the ability to do full transaction control. In stored functions, you could use save points, but you can't control the outside transaction that sort of runs everything. So that's also like a big thing. In particular, I've noticed, I do a lot of work with people who migrate from the big expensive proprietary databases into Postgres. And there are a lot of patterns there, and a lot of, in particular, things like loading jobs and ETL jobs kind of things that really use this heavily. You've usually been able to accomplish the same thing in Postgres previously, but this makes it a lot easier, both from the migration and the actual implementation side of things. So let's take a look at backup and replication. You all do backups, right? No, you don't. I mean, come on, really. There's been no super major things, but a number of incremental improvements. Postgres adds something called the ability to advance replication slots. Primarily, this is not something that you will use directly. It is something that your replication management tools will be using. Tools like Patroni or Rep Manager or all of these things around Postgres. The idea is we have these replication slots that keep track of where different nodes are in the replication stream. But if you have, say, you have a primary and a standby, and then you do logical replication to a different machine, and then you get a failover between your primary and the standby, it will actually lose track of the logical replication step by default, because the replication slots are gone. And what you could do previously is, well, then I create the replication slot on the standby as well, and the logical replica will work just fine. Except now your standby will instead run out of disk space because you have a replication slot that blocks disk reuse. And there's previously been no way to move this replication slot without actually replicating the data. So there were workarounds where let's create a replica that pipes all this data to DevNull, which is not really productive. The idea here is very simple. You can now at regular intervals just move all your replication slots across a cluster of many machines to be in sync. They never have to be exactly in sync, but they close enough in sync within a couple of megabytes so that you don't run out of disk space. So this makes the kind of like mixed clusters of mixing physical and logical replication a lot more manageable. Speaking of logical replication, who's using logical replication in Postgres 10 or 11 today? That is surprisingly few. That was one of our headline features. Come on, guys, you should be using it since 10. It took a lot of work to build that. One of the things that we couldn't do in Postgres version 10 is logical replication did not replicate truncate. It would replicate your insert, updates, and deletes, but if you actually did truncate on the primary, the table would go empty on the primary, but it would keep the data on the standby because the truncate wasn't replicated, which is usually not what you wanted. In 11, it does. You can turn this on and off on an individual publication. You can say, for this table, I want truncates to replicate. For this, I don't want them to replicate. Logical replication has a lot of non-standard use cases where that actually makes perfect sense. But since in most cases it doesn't make sense, it will be on by default. So if you just create a publication or if you upgrade your Postgres version 10, your logical replication will just start replicating truncate. It will just start working. And if you don't want that, you have to explicitly go turn it off with alter publication. Another more on the physical replication side, and in particular on the backup side, base backups taken through the Postgres internal protocol no longer include unlogged tables, which makes a lot of sense. The unlogged tables are tables that don't go into the transaction log, so by definition they're not crash safe. But they're useful for things like large data loading job. You might load the data into an unlogged table and then do some processing and merge it into a regular table, for example. And unlogged tables work the way that when Postgres crashes or restarts, it just wipes the contents of the unlogged table. It comes up as an empty table because it's not crash safe. We can't trust the data, so we delete the data. The table is there, but it's empty. And what we did for backups was we included this table in the backups. Then we restored this table on your restore, and then as you started Postgres, we deleted it again. And particularly given that these are often used for large loading tables, that's kind of a waste of space in your backups if the only thing that we guarantee is we're going to delete them as soon as we start up. So we no longer do that. And similar thing for temp tables, which are even more apparent, right? Temp tables, when you do create temporary table, well, if you disconnect, the table gets deleted. That's how it's supposed to work, right? So by definition, if Postgres restarts, it gets deleted. If you restore from a backup, it gets deleted. But it used to be included in the actual backup and get deleted on the restore instead. So yeah, I've seen cases where this saves a lot of disk space in the backups that were just completely useless. The other thing that backups do now is that they will validate page level checksums as the backup runs. If you've enabled page level checksums on Postgres, unfortunately this is something that is not enabled by default, and you can only enable it currently on initialization of your database cluster. So when you run initdb, you have to decide to use them. You can't turn them on after the fact. You probably should turn them on in almost every single case, because you want to know if your data is corrupt. Now, the way that this worked previously is whenever Postgres reads a disk page, so you run a select query or something, it reads the page from disk, it validates the checksum. But if you have tables that are very infrequently read, or portions of tables that are very infrequently read, you can get bit rot in those files, and you would never know, because Postgres didn't validate the checksum. Now, when we run backups, we read all your data, right? That's kind of, you have to do that. And the expensive part of validating the checksums is reading the data. Actually calculating a checksum across an 8K block is very, very cheap today. So what we're doing now is just whenever we read the data for backups, as soon as we read the block, we validate the checksum of it. And this way, because backups will include your infrequently used portions of the database. So it will then notice that your data is corrupt. Now, it can't fix it for you, unfortunately. But it can tell you, hey, you have corrupt data in this table. The idea being, well, hopefully you still have your previous backup. And you can go restore from your previous backup and use your log archive to basically roll past the corruption and just remove the corruption. But if you only get to know it 6 months later when somebody queried the infrequently queried table, you may not have a 6-month-old backup, and you may not want to restore a 6-month-old backup. Right? So it's all about getting the information sooner. So that you can properly handle it while it doesn't cost you so much to handle it. But again, checksums are not enabled by default, but I do strongly encourage you to consider enabling them. We are looking at, in the upcoming version of Postgres, there will most likely, it's not been committed yet, but most likely there will be toolage available to enable and disable checksums. Unfortunately, enabling checksums on a large database is very expensive because it basically has to rewrite the whole database. But disabling checksums will be very cheap. And there are actually tools you can get, they're just not part of Postgres today, that will safely turn off checksums on a running cluster. Right? You just have to stop Postgres, run a tool that runs in less than a second and start it again to turn it off. Which I find a good reason for, well, just turn them on by default because it's easy to turn them off. It is not easy to turn them back on. They do create a bit of overhead. In my experience, nowhere near enough overhead to be a problem, versus the problem of realizing too late that you have disk corruption. And if you trust your hard drives or your SAN or your cloud provider not to generate disk corruption, then good luck with that. Far too many people do, and it can be very expensive. Okay, let's talk about a few things around performance, right? Everybody wants things to run faster. Almost everybody wants things to run faster. Postgres 9.6 added parallelism, so the ability to run parallel query, use multiple CPUs for the same query. Right? Up until 9.6, you had the matching of one connection, one CPU, which becomes a problem with modern machines with hundreds of CPU cores, and you go like, yes, you can use one. Sometimes we could use two, one for a background job and one for your query. As of 9.6, we could use multiple ones, but in practice, it didn't really help that much because it limited the number of queries, like the number of types of joins, the number of types of scans. For example, in 9.6, you couldn't parallelize a query if it involved an index scan. Postgres 10 made it really, really useful because it removed most of these restrictions. I can actually say, I think I'm still at a point that none of our consulting customers have actually had any use for parallelism in 9.6. And probably 80% of them have had use for parallelism in 10. So that's when it became useful. Now 11 adds a few more things that makes it even better. There are a bunch of general enhancements that just sort of silently makes it better and you don't have to care. We've added something called a parallel append plan nodes. Doesn't really help you know that, it just runs faster. And we have something called parallel aware hash joins. Whereas previously, if you were running a hash join, it supported parallelism, but it did basically, if you parallelized it across 4 processes, in a simplified version, you can say it ran 4 parallel hash joins, they built their own hash tables, they were completely independent, just on different parts of the table. With the parallel aware hash joins, they all share a hash table, so you can get a much bigger hash table, much more efficiency, by still using it across multiple processes. And these are all things that you don't have to do anything about. This is just like literally run 11 and your queries will be faster. That's the best kind of enhancements, right? We now have the ability to do parallel create index. Because, well, create index is a DDL command that usually takes a long time if you have a lot of data. And it's very often CPU bound. Unlike many other DDL commands which are blocked by the amount of I/O you can do, create index in its simplest form, well, it loads your whole table, it sorts it, and then it writes it out as an index, right? Obviously, if it's a large table, it's not quite that simple, but the basic principle is that. And sorting takes time. Sorting is expensive. So we can parallelize that. We have a new parameter called max parallel maintenance workers. Say that fast 4 times. The default value is 2, which means that your create index will use 2 CPUs to run. There are definite cases, particularly if you're like loading from a dump or big load jobs where you don't really care about the effect of the rest of the system, where you will want to increase this quite a lot, like 8. You can scale out across 8 CPUs, for example. Problem is, of course, if you run your create index across 8 CPUs, you probably kill everybody else on the system. Right? So you might not want to change that globally for everything, but it's something that is worth considering. Now, unfortunately, parallel create index only works for B-tree indexes. The most expensive index I think we normally create today in Postgres is, for example, PostGIS geographical indexes. They can't be parallelized. Well, yet, but they can't be parallelized in 11. Hopefully we'll get that sorted, but it's not there yet. So parallel query was the big headline feature of Postgres 9.6, right? And it made really useful in 10. The big headline feature in Postgres 10 was partitioning. And in my view, sort of just like parallel query was not really that useful in 9.6, partitioning is not really that useful in 10, but it builds a lot of important infrastructure. And 11 for partitioning is like 10 for parallelism. It starts delivering, like now is when you get all the benefits. There were a lot of things. Declarative partitioning with the syntax and basic functionality was in 10. So if you were using the previous sort of manual partitioning and you're on 10, it's definitely worth migrating to this one. But it fundamentally works exactly the same as before, just with prettier syntax. But it has all the same drawbacks, almost. It fixed like one thing. Now 11 fixes a bunch of things. Number one, it adds support for default partitions. In Postgres 10, if you added partitions and you tried to insert a row that didn't match anything, you would just get an error. In 11, you can add a partition like this, partition of P default, and every row that doesn't match anything else will go here. One of the absolute biggest thing is if you did, in previous versions, if you did an update on a row so that the partitioning key changed so that it would end up in a different partition, it would just fail. You couldn't do that. Once you'd put a row into a partition, it would have to stay in that partition. In 11, you can just update it. It'll get moved to the other partition. It'll just work. What you had to do previously was basically manually delete it and then reinsert it, and then it would work. But that comes with other, it's a lot more work. It's tricky. And the whole point of partitioning is that it's supposed to be transparent. Right? It's supposed to look like one table to your application while actually being 100 tables underneath. And having to not do update is not really transparent. It's still not perfectly transparent, but it's much closer. Now you can still get some concurrency issues because in practice what it does is a delete and then an insert. But they're not as bad as they were before, but there could, in theory, you could do the delete and then somebody else does the same thing at the same time and things like that. Another limitation and advantage is that you had no way to actually, once you'd partitioned your table, you couldn't create indexes across the whole thing. You would have to create indexes individually in each partition. 11 adds what we call local partitioned indexes, which is you can create an index on your master table, which will then automatically get created across all of your partitions. And most importantly, if you create a new partition, it will also get the index. So it keeps going. Now you can still add individual partition indexes as well, because maybe if you have time-based data, your old partitions can afford to have a few more indexes because they're mostly read-only. So you can still have them, but you can create these indexes that will spread out to all of them, including future ones. And you can actually now create a cross-partition unique constraint as long as all partition keys are part of the constraint. Because then Postgres can know that this is actually unique across all of the partitions by the fact that it is also unique on the individual ones. Now this is the foundation for being able to have a foreign key pointing to a partition table. Unfortunately, we can't do that yet. We're hoping to have that. It's a patch that's being reviewed for Postgres version 12, and just a couple of days ago, I think we heard the report saying it's most likely going to be in there, but it's not there yet, so no promises. Other things around the partitioning, insert on conflict. Use that, the upsert method, insert on conflict, do update, or insert on conflict, do nothing. It didn't work on partitioning. Now it does. Okay, that's good. That's also one of those. It's not transparent if some things don't work. Another really big thing is we have a new and better way of doing partition pruning. Partition pruning is when the query planner and executor figures out that, oh, I only need to look at one of your 100 partitions, thus things run faster. That's one of the main reasons we do partitioning, right? The way that this used to work is that Postgres did this in the planner. So when you submitted your query, it would look at the query, it would look at the parameters of the query, and based on that data, it would figure out which partitions to scan. And there were a lot of cases where that could fail. For example, if you had a query, where x equals, or where x in, and put a subquery there, then the planner has no way of knowing what the subquery is going to return, so it will scan all partitions. And that defeats a lot of the point. The way that 11 does it is it does the old pruning first, so it looks at the query and deletes it, removes all the partitions it can, but then it runs a second run of pruning once it's in the executor, and it can run the subquery. It can get, oh, I got these numbers back, and then it runs a second pass and deletes a new bunch of partitions. So there's a lot of types of queries that would previously just give you a scan across every partition that will now just scan the partitions that you need. Which again is one of the main reasons that we use partitions, right? It's to be able to scan them and to be able to delete them. We've added hash partitioning. Previously we had list partition and range partition. Now you can say hash partition, which is the idea you pick a column and you say, I want this in 4 partitions, have the system distribute it evenly between these partitions. As good as evenly becomes based on the hash value. But if you have a good hash function, it will be pretty good. So in this case, previously you would say, partition by hash of I instead of partition by list or range. And then you still have to create the partitions. So here I say, well, create this partition for values with modulus 4, remainder 0. Then you get a modulus 4, remainder 1, 2, and 3. There's your 4 partitions. And you can subpartition it as long as you keep the ratios workable and get into more advanced. And this is for just sort of, if you just want to distribute your data maybe across multiple storage devices or something like that, you can put your partitions across them. We've added partition-wise joins, which is basically if you have 2 partition tables that are partitioned on the same key and you join on that key, then you can actually execute that query as joining partitions individually to each other instead of just doing one partition across all the others, then one partition across all the others. It has to be a join on the complete partition key, but if you do that, the planner can figure out and see that, okay, this is the special case where you can run these as many simple operations instead of one more complicated operation. This is turned off by default. So there's a configuration like enable partition-wise joins equals false by default. And the reason for that is that it makes planning of your queries on partition tables more expensive. Like there's a cost involved in figuring this out. But if you have a workload where you know that you're actually doing this, you're joining tables that are partitioned on the same keys, then you should definitely consider turning this on for those particular sessions by just issuing the set enable partition-wise join equals on or true or 1 or whichever one you prefer. So that's one of the few of these that you actually have to turn on. Most of the other things are just there. We've added something called partition-wise aggregates. So again, if you do a group by, and you group by on your partition key, or part of the partition key, the partition key is part of your group by, then you can actually run the group on the individual partition and bring up the summary values, and then run it again on those, thereby making the scan much more scalable. For example, the sum of a bunch of rows is the same thing as the sum of the sums. Then it's based on that as long as you have the partition key. There is some other sort of general performance. The particularly big thing you'll see here is Postgres now has JIT compilation of expressions and JIT compilations of what we call tuple deforming and forming, which of course everybody knows exactly what it means, right? It uses LLVM. So the availability of this actually depends on your packaged Postgres. What's normal is you may need to install an extra package. For example, if you're using the Yum distribution on Red Hat or CentOS, there's a separate package that you install on top of your Postgres that just enables this. And what it does is, for example, it does expression inlining, which is if you run like big data warehousing queries. The way the Postgres works is you run the expressions normally in software, and it's not super optimized for the CPU because it can't be, because we have all sorts of interesting data types. And what it'll do is when the cost goes above a certain cost, it will trigger and have LLVM byte compile this particular expression, take this column plus this column divided by this column, and turn that into machine code, and then run your query with that, which, if you're processing a few 100 million rows or something, that can be massively much faster. I've seen benchmark of, ridiculous numbers, like 90%. That's obviously a constructed benchmark. There are also cases where it will be slower, right? Because it takes longer to do the compilation than it takes to run the query itself. the system tries to only enable it when it's beneficial. It will not always succeed. There's a tuning parameter that you can tune how high should the cost be before we turn on JIT. But particularly if you are running like data warehousing or something like that, something that processes large amounts of data, go look at installing those packages. It will definitely make things faster. If what you're doing is simple OLTP, you're never looking at more than 2 rows at a time, it's probably not going to make a fundamental difference. It's for the cases where you run a lot of expressions fast. So that's a lot of features, right? Then we probably covered, I don't know, 5%? But hopefully we covered all the big ones. There's always going to be a lot more things, right? There's a lot of smaller fixes. There are a lot of performance improvements that we can't go through. If there are, so I usually say, if there's any of the Postgres developers in the room and I didn't mention your feature, I'm sorry. I'm sure it's important because all the features are important. They're important to somebody. They're important to somewhere. So please help. We do still need your help. Postgres 11 has been released, but we still need your help out here to download and test it and run it. And some of you are already. That's awesome. Now you need to go test the new features that you maybe didn't know existed. Download your packages, run your application, and let us know. We're still very much interested in feedback on things like, in particular, in this workload, JIT made things slower, or the parallelism doesn't actually work, and things like that. We believe we're in pretty good shape on the fact that we still deliver the correct responses, but there can definitely be performance regressions under certain workloads where we may need to tune default values of parameters and things like that. And if we get that feedback in early, it makes it easier. You don't have a version of Postgres 12 to test on yet, but feedback that you give us on Postgres 11 now is going to make it into Postgres 12, which you're going to see in about 6 months, most likely. Development ongoing. We hope to have it ready in, let's call it September. And we'll see what happens. We hope to have it ready this year. We all know, time plans and things. So that's all I wanted to mention. I want to thank you very much for showing up and staying awake on the second day of FOSDEM. That's pretty impressive. If you have any further questions, I think we have like 3 minutes or so before we have to get out. And after that, feel free to just grab me outside for any further questions. But anyone? Yes?
Is it on? Yeah. I believe you said for the partitioning that there is now a feature where it will run a subquery first and then replan based on the results.
So that is not entirely correct. It will not replan things based on the result. It will rerun the partition pruning. So the only part that runs is the whole, I know that I don't need to scan these partitions over here because based on the things that came up, I know all my data is over here. It doesn't actually change the query plan.
Oh, that's a shame. You see a lot of cases where that might help, actually.
That would definitely be an interesting addition, sort of generic replanning when you start running a query and realize, this is not good. But that's not something we have today, no. Sorry. Anyone else?
Any questions?
We got one in here?
How should we take care of indexing when we use window range operations? Do we preferably have an index on the field that is used for the ordering, as I guess, but do we have other things to take care about?
You mean for the window query
Yeah,
style?
what you presented earlier. Yeah.
It's really the same. What is running underneath is a select with and order by. So you need the same kind of indexing considerations as you would if you just did that select with an order by. Okay. So if you may also have an outside where clause and then combine it with the order by for an index like that. But at the bottom, it's the same kind of indexes that you would have for
existing indexes would be used efficiently for this kind of operation. We don't have anything on top to take care of.
Exactly. Existing indexes will absolutely be used. Now, of course, if you run it across your entire table, it's probably not going to use the index, but it didn't do that before either. Yeah. Because that becomes too expensive. But it's the same considerations as you had for sorting that kind of data before.
Okay.
Yeah.
Thanks.
Thank you. Yeah. David, run.
Okay, thank you for transaction and procedures. Now we can build the ETL process without any third-party system. And I would like to ask about small thing, calculated field. To have calculated field in tables like in MySQL, to have indexes in this field, and
Yes, so
do
we
you think?
I think the standard calls it a generated column, right? Where you define that this column is going to be x plus y, right? We don't have that. What you can do in Postgres, you can create an index on the expression, right? And that will be used if you're querying it. And then you can create a view on top so that you read it through the view. But there's no way to materialize it into the table unless you want to write the trigger.
Thank you.
Yeah. Thank you. I think it's time to kick everybody out and change to the next talk. Thank you very much.